Hello students, welcome to EPG Pathshala. I am Rima Gupta from University of Delhi and today we are going to discuss about the module that is Defect Chemistry Part 1 and this is from the paper Ceramics. So after completing this module, you shall all be able to understand the fundamentals of point defects, the nomenclature of the defects in ceramics, and the defect reaction in stoichiometric solids. So before starting this module, let us discuss about the basics of the defects. So the materials in general consist of defects which can be divided into a variety of categories such as point defects or 0D defects, line defect or one-dimensional defect or two-dimensional defect. So these defects play an important role in determining the properties of ceramic materials, and in this context the role of point defect is extremely important. So in this module we will be learning about various point defects, role of stoichiometry, that is cation and anion excess, and deficient, the role of foreign atoms in the defect chemistry also. So subsequently we will adopt a simple thermodynamic basis for calculating their concentration in equilibrium, and then we will extend the Gibbs-Duman relation for the chemical systems to the defect in ceramics, considering them to be equivalent to the dilute solution. So an approximation will be considered which is fairly valid. This will lead us to the determination of defect concentrations as a function of partial pressures of oxygens, which is very much important exercise to establish the defect concentration versus partial pressure oxygen diagrams and so on. So the first topic which we will be discussing is point defects. Point defects are caused due to the deviations from the perfect atomic arrangement or stoichiometry. These could be missing lattice ions from their positions, interstitial ions or substitutional ions which are impurities, and valence electrons or holes. Usually the point defect in metals are electrically neutral, whereas in case of ionic oxides, these are electrically charged. So if we talk about ionic defects, so the ionic defects occupy lattice positions and they can be either of vacancies, interstitial ions, impurities and substitutional ions. Whereas if we talk about electronic defects, the electronic defects are the deviations from a ground state electron orbital configuration which give rise to such defect when valence electrons are excited into higher energy orbitals or levels. So this leads to the formation of electrons or holes. The electronic defects are present in most oxides and are easily understood. Hence, most examples in this module are of oxides. Kroger-Wink notation in a metal oxide. So here we are representing the metal oxide with MO, where M is corresponding to metal and O corresponds to oxide. So in case of regular sites, the normal or regular occupied metal or cation site is represented by MM. So here's M is subscript of capital M. The normal or regular occupied oxygen or anion sites is represented by OO. Now, if we talk about point defects, the notations of various vacancies interstitials are shown here. So for the oxygen anion vacancy, it is VO. For metal cation vacancy, it is VM. Oxygen anion interstitial is OO. Metal cation interstitial is Mi. Vacant interstitial site is Vi. Foreign cation is represented by MF. Foreign cation on regular metal site is represented by MFM, where Fm is the foreign cation on metal site. Next is the foreign cation on interstitial site. It is represented by MFI. A normal cation or anion in an oxide with zero effective change is given by M with subscript M and superscript X, or O as subscript O and superscript X. The next is charged oxygen vacancy, which is represented by VO star or VO star star. So here this star represents one positive charge. The charged metal or oxygen interstitial is Mi star star or OI dash dash. The neutral cation and anion vacancies are similarly represented by VMX or VOX, and the electrons and holes are represented by E and H. Now comes defect reactions. So there are some rules for writing the defect reactions. So the first is the ratio of regular cation and anion sites is always constant. Moreover, the mass balance should be preserved. The next is electrical neutrality is to be always preserved. Then both ionic and electronic deficient compensations, or we can say both ionic and electronic defect compensations, are possible, which are determined by the energies, and we will assume the complete ionization of the defects to determine these quantities. Defect structures in stoichiometric oxides. The charge point defect is a defect which ready to be ionized and provides a complementary electronic charge defect. So various combinations are possible, such as cation anion vacancy. So here we are resembling cation vacancy by Vm and anion vacancy by VO. So this result in Schottky, whereas the second possibility is vacancies and interstitial ions of the same kind, which leads to Frenkel defect. Moreover, the misplaced atoms, that is MO or OM, interchange resulting to VO and OI or VM, and Mi divided by Vm plus Mo. So the vacancies and misplaced atoms for the same kind of atom will be there, or interstitial and misplaced atoms, that is OI and MO. The another possibility is interstitial atoms, that is Mi and OI, that is cation interstitial and anion interstitials. Now first is Schottky disorder, which we will be discussing in this slide. So the Schottky disorder is a defect which normally forms at the outer or inner surfaces or dislocations. It eventually diffuses into the crystal, unit equilibrium is reached. So you can see on the left hand side, so this is the example of Schottky disorder. So some of the examples for it is NaCl, that is sodium chloride, MgO, that is magnesium oxide, corundum structures and rutile structures. So the defect reaction is written as O or null gives Vm double bar plus VO double star. So let me recall that Vm double star correspond to charged metal vacancy, whereas M double star correspond to charged metal or oxygen interstitials. So this defect is preferred when cations and anions are of comparable size. So some of the other examples for such defect is rock salt structures also. Now the next disorder which comes into picture is Frankel disorder. So on the left hand side, students, you can see the Frankel disorder. So this effect can form inside the crystal. It forms where cations are appreciably smaller than anions, and the defect reaction is written as O, that is null, gives Vm double prime plus Mi double star. Or in cases where anions form disorder, then it is called as anti-Frankel. Corresponding, the defect reaction in that case would be null, that is 0, gives Vo double prime plus Oi double prime. So some of the examples of compounds showing this defects are AgBr, that is silver bromide type compounds such as AgI, AgBr, etc. However, the examples for anti-Frankel are CaF2, that is calcium fluoride, and strontium fluoride, that is SrF2, and barium fluoride, that is BaF2. The next is intrinsic ionization. So, the thermal creation of electron-hole pair is intrinsic ionization, and this intrinsic ionization can be depicted as null is equal to electron plus hole. Now let us discuss the defect structures in non-stoichiometric oxides. Mainly, there are two types of deficiency. First is oxygen deficient or excess metal. Second is metal deficiency or excess oxygen. So the examples of oxygen deficient can be MXOY minus del or MX plus del OY. Whereas some of the example for metal deficient will be MX plus del OY or MX or Y plus del. So here non-stoichiometry necessitates the presence of point defects and extent of non-stoichiometry which determines the concentration of defects. In such oxides, electrical neutrality is preserved through formation of point defects and electronic changes. The intrinsic ionization is always a possibility in this case. Therefore, the oxygen deficient oxides can also be there, where the formation of oxygen vacancies or metal interstitials or both are possible. Now let us first discuss if the oxygen vacancies are the dominating defects, that is the oxygen deficient oxides. So such defects are depicted by MO2 minus X, where X is the extent of non-stoichiometry, and overall the reaction is MO gives MO2 minus X plus X by 2 times O2. So here the reaction is reversible reaction, that's why the arrow is in both the direction. Due to loss of oxygen, possible defect reactions would be: first is electronic compensation leading to creation of oxygen vacancies and of electrons. So the guiding reaction is OO gives VO double star plus 1 by 2 O2 plus 2 electron. The second possibility is ionic compensation, which leads to the formation of oxygen vacancies and reduction of metal ions on their sides. So the reaction for such possibility is OO gives VO double star plus 1 by 2 O2 plus 2 times MM bar. Now let us consider if metal interstitials are the dominating defects. Then what will happen? The materials will be depicted as M1 plus Y O2, where Y is the extent of non-stoichiometry. So the possible defect reactions are, the first is ionic compensation leading to the formation of metal interstitials and reduction of metal ions on their sides. And the reaction is MM gives Mi star 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 plus 4 times MM prime. Or the next possibility is electronic compensation leading to the formation of metal interstitials and free electrons, where the reaction is M gives Mi double star plus 4 times electrons. So here the 4 electrons are there. So the creation of quasi-free electrons, that is extra charge, is represented as M prime, and the conduction occurs due to transport of electrons, and such type typically present in N-type of conductors, and some of the examples for that are titanium oxide, that is TiO2, zirconium oxide, that is ZrO2, cerium oxide, that is CEO2, niobium oxide, Nb2O5, and so on. Now let us discuss about the metal deficient oxide. So metal deficient oxides are formed either due to metal vacancies or oxygen interstitials, that is excess of oxygen. The formation occurs typically at the surface. So first we will be discussing about if metal deficiency is dominating defect, then the possible defect reaction will be 1 by 2 O2 gives OO plus VM double prime plus 2H dot. So here in this case there is a hole formation. So the another possibility, or we can write the same reaction as 1 by 2 O2 gives OO plus VM double prime plus 2 MM star or dot. So in this case there is metal oxidation leading to the formation of P-type oxides, and this is due to the conduction of holes. And some of the examples showing such behavior are magnesium oxide, that is MnO, nickel oxide, that is NiO, cobalt oxide, that is COO, and iron oxide, that is FeO, and so on. So this slide is in continuation for the metal deficient oxides. So if the oxygen interstitials is dominating defect, then the oxides are depicted by MO2 plus X. The oxygen interstitials can form due to the following reaction, that is 1 by 2 O2 gives OI double prime plus 2H dot. So here also there is a formation of holes, and this occurred due to the conduction of holes and resulting in P-type conductor. So some of the examples are UO2. Now comes the dissolution of foreign cations in an ion. So let us take the case 1. The case 1 is parent oxide is MO and foreign oxide is MF2O3. Now the following scenarios are likely to present. The first is MF3 plus occupies M2 plus sites in MO, giving rise to an extra positive charge on the metal site, and a free electron according to the following defect reaction occurs, that is MF2O3 gives 2 MFM plus 2OO plus half O2 plus 2 electrons. Alternatively, for a metal deficient oxide MO creates metal vacancies, which is in this reaction shown below, that is MF2O3 gives 2 MFM plus 3OO plus VM double prime. However, for an oxygen deficient oxide, the oxygen vacancies are compensated as VO double star plus MF2O3 gives 2 MFM plus 3OO. So in this, the third reaction results in the reduction in vacancy concentration, while the first and second reaction results in increase in the electron concentration or metal vacancy concentration. The fourth type is the reaction 1 for a p-type conductor, which can be alternatively expressed as 2H, that is holes, plus MF2O3 gives 2M FM plus 2OO plus half O2. Now, the case 2 is parent oxide is MO and the foreign oxide is MF2O. So, students, you can take this as an exercise or homework, and it is recommended for you to carry out this exercise. So, students, let us summarize what we have learned in this module. So, in this lecture, we have learned about the existence of point defects as a reality in the materials and that their presence can be well studied using the defect reactions. And these defect reactions are very much similar to the chemical reactions. So, the point defects can be neutral, or it can be charged, or it can be neutral as well as charged defects in most materials, and they are denoted by Kroger-Wink notation. So, in this module, we read that in Kroger-Wink notation, for the regular sites, the normal and regular occupied metal or the cation side is represented by MM, and the normal and regular oxygen sites are represented by OO. So, oxygen is for O and metal is for M. Next, in the chronic Wink model, we have read that there are various point defects which have their own notations. For examples, for the oxygen vacancy, we are representing it by VO. For metal vacancy, it is VM. For interstitials, we are representing by I in a subscript. So, if it is an oxygen interstitial, it is OI, and if it is metal interstitial, it is MI. Moreover, we have read that the vacant interstitial sites are also there, which are represented by VI. Similarly, we have read that there are foreign cations and foreign interstitials which have the same representations as MF or MFI. So, students, let me recall that these notations we have used in over the complete module for representing the type of cation, a type of defect, or a type of interstitial. So, these representations are used in the reactions which we have read in this module. So, the guiding principle to form a point defect is that a solid has to remain charge neutral. So, the point defect formation in a stoichiometric solid takes place by formation of anion and cation vacancies in a stoichiometric amounts, and this is called stoichiometric defects, whereas by formation of Frankel defects through formation of vacancy of cations or anions and an interstitial of the same ion. So, to avoid confusion, I am repeating that the Schottky defect is due to the formation of anion and cation vacancies in stoichiometric So on the other hand, we have also read that in non-stoichiometric solids, defect formation also give rise to a compensating electron or hole or oxidation or reduction for maintaining charge neutrality. We also looked at how impurities in ionic solid can change their defect chemistry and which can be used in a useful manner. Thank you.